This conference will now be recorded.
So, very good evening, students. We had last day discussed about velocity, speed, what is average speed, instantaneous velocity. Also, we had discussed somewhat. We'll just have a short recap and graphical representation, which I did not discuss on that day. Today, I'll discuss the graphical representation of instantaneous velocity, and then I'll move on to the next topic, that is acceleration today. So, as we had discussed, the instantaneous velocity at any instant of time is defined as the limit of average velocity, as the time interval delta t becomes infinitesimally small. Okay, see, this is the mathematical expression for that. So we know the average velocity is delta x by delta t. Okay, the change in the position over an interval delta t. Excuse me. And if we take the limit of delta t tending to 0, that gives my instantaneous velocity. This is the mathematical way of writing. And you know, this particular portion, when delta t tending to 0, according to the language of calculus, we can write as total derivative del dx by dt. So up to this we had discussed last day. Now we'll see the graphical representation of instantaneous acceleration. So this part we had not discussed that day. So we'll start from here. Okay. Look here. This is the position time curve, position in the vertical axis and time in the horizontal axis, and position is measured in meter, time in second. Now, if you remember the curve, where the car was moving in a straight line, it was picking up its speed up to 8 seconds. That we had discussed this curve somewhat. Then it attains a uniform velocity. Uniform velocity and continues till 18 seconds, and thereafter the car starts applying brake such that the velocity decreases and it goes up to 20 seconds, and after 20 seconds the car stops, so the position remains constant with respect to time. Now we want to calculate instantaneous velocity. We want to represent instantaneous velocity in the position time curve itself. So how do you do that? For our convenience, we had taken the part of this curve till 8 seconds. We have zoomed this curve up to till 8 seconds. We have zoomed it up. Look here. This obviously it is shown in the graph till 6. So we have zoomed the curve from 2 seconds to 6 seconds, 2 to 6 seconds, the same curve here. So we'll see here how instantaneous velocity can be defined graphically or geometrically. So we know that average velocity is defined graphically or represented graphically as a line joining the 2 points, slope of the line joining 2 points on the position time curve. I'll just repeat this. So average velocity was graphically represented as the slope of straight line joining 2 points in the xt plot. Okay, so this is what we have learned last day. So today we'll, because this we have to remember, because see here we'll be taking the limit of delta t tending to 0 for the average velocity only, delta t tending to 0 for average velocity. So suppose I have to calculate instantaneous velocity or just velocity at any time t is equal to 4 in this curve. In this curve, I have to find out that instantaneous velocity means velocity of the car at any instant. So at 4th second, I want to calculate or see the velocity of the car at 4th second of its motion. Now look in this curve, if we want to do that, first of all we have to find out the average velocity, then we have to decrease the time interval delta t tending to 0 towards 0. Then we'll be able to get the proper representation, a proper graphical representation of instantaneous velocity. Now look, this in this curve, I just take interval. First I take interval 2 seconds. Okay, 2 seconds. Keeping this 4th second in the middle. See, this is the middle. So 2 delta t 2 second means, see, one point is here at 3 second and another point P2 at 5th second. Okay, 5th second. Yeah, near around 5th second. So the time interval is delta t is 2 seconds and the point P where I have to calculate the instantaneous velocity is in the middle of this interval. Now, according to the definition of or representation of average velocity in position time curve, the slope of P1 P2 line, P1 P2 line, slope of P1 P2 line will give you the average velocity in this delta t. Delta t is equal to 2 seconds interval. I hope you agree with me. I'll just repeat it here. So the average velocity, I'll write V average. Average velocity in delta t equal to 2 seconds will be actually slope of P1 P2 line. Now what we have to do to get the instantaneous velocity, we have to reduce the time interval. Then what I am doing, I'm just reducing the time interval from delta t 2 seconds to 1 second. 1 second. So if I reduce the interval from 2 second to 1 second, look, this PQ, this P1, P2 line, that becomes Q1, Q2 line in this XT curve. See Q1, Q2 line, this one. That means in between 3.5 and 4.5. So this will give you 1 second time interval, keeping 4 second in the middle. Now, average velocity for this time interval is the slope of Q1, Q2 line, okay, Q1, Q2 line for the interval delta t 1 second. Okay, I hope you are understanding. Now, according to the definition of instantaneous velocity, I have to make this delta t 0. Now, if I just decrease further and further and further, and if I tend this delta t interval towards 0, if I just approach towards 0, slowly towards 0, look at some time your this Q1, Q2 line becomes a point, okay, just a point P, exactly at 4th second, okay, 4th second. It becomes a line P, sorry, point P. Oh, I'm sorry. This Q1, Q2 becomes a tangent T1 here. I'm sorry, this becomes a tangent T. So if you further and further decrease the time interval to 0, towards 0, when the time interval is very near to 0, this Q1, Q2 line becomes a tangent T1 at the point P, which is exactly at 4th second. Okay, so how do we define graphically instantaneous velocity? It is the slope of the tangent at any time on the xt curve or position time curve. So what will be the formal definition? So graphically, instantaneous velocity is represented as the tangent slope of the tangent, as the slope of the tangent at that particular instant of time. So graphically, instantaneous velocity is represented as the slope of the tangent in the xt curve, in the xt plot or graph or curve at that particular instant of time. So where it is t1 is the tangent, so I have to find out the slope of this t1 tangent at p, exactly at that instant, 4th instant, 4. on this curve. So this is how graphically we can represent the instantaneous velocity. Okay, now we'll move on to the next topic for today's discussion. Before that, I'd like to show you how do you draw velocity time curve from a position time curve. Look, as we have understood that till 0 to 8 seconds, this is a position time curve, this is velocity versus time curve. This is position versus time curve. So we can draw, just by looking this, we can draw the velocity. If this curve is given, position time curve is given in your exam, you can immediately draw this velocity time curve. How? You have to look this intervals, particular intervals, and see where the motion is what. So in this case, look, 0 to, in between 0 to 8, as I said, the car was picking up its speed. So the speed is increasing uniformly over here. So if the speed is increasing, look, up to 8 seconds, this is the thing. So it goes like this. So it is increasing like this it is increasing, and till 10 seconds it takes to pick up a uniform velocity. So look here, till 10 seconds, within 10 seconds, till 10 seconds it increases. This is actually increasing increasing velocity, okay, or velocity increasing. And look this, after 10 to till 18, this has actually 18, below 18 till 18, it has uniform motion. Uniform motion means it has uh, constant velocity. So that's why here till 18 it was constant velocity, or maybe you can think till 20 it is constant velocity. This is constant velocity. And since the car applied brake after 20 seconds, it will start decreasing its velocity, and after 18 seconds it starts applying its brake, so it will lose the velocity. So you can see this is the decreasing velocity. This portion, and exactly at 20 it becomes 0. So here velocity becomes 0. So this is how any graph you have to analyze. Okay, you can analyze your graph like this. So if we'll see, if we would have been asked to find out the acceleration versus time curve from this position time curve, there also we'll be able to draw an acceleration time curve. Okay, from this position time curve itself, we'll show you how to do that in the next few slides. Okay, so we have already learned what is velocity, what is speed, what is average velocity, instantaneous velocity, and instantaneous speed. Instantaneous speed is actually the magnitude of the instantaneous velocity. So what is instantaneous speed? Instantaneous speed is magnitude of instantaneous velocity. Okay. Now today we'll learn what is acceleration. So velocity, average velocity, V average, or I'll write by symbol. So V average was giving change in position. change in position over an over a time interval then instantaneous velocity simply written as v. It was giving you the change in position at each instant or every instant of motion. Now question comes whether velocity also changes with time. Now question is whether velocity also changes with time. This is our question now. After learning what is instantaneous velocity, what is average velocity, now the question comes whether velocity also changes. If changes, then how to define change in velocity? Is there any new parameter to define this change in velocity or represent change in velocity with respect to time or anything? Change in velocity? The answer is yes, that is the acceleration, denoted by small a, sometime f also. Some cases people use f, acceleration. So in our book, so in our lecture we'll be using throughout acceleration. We'll be denoting acceleration as a. Now look, during Galileo's time there was a confusion. Now we know change in velocity with respect to time is defined as acceleration. So what is acceleration? Change in velocity with respect to time, or in a single language I can write, simple language, rate of change. Okay, I'll just remove some of this. So the rate of change of velocity, or we'll write time rate of change of velocity. Maybe that will be the perfect sentence to say. Time rate of change of velocity is defined as acceleration. Or in other words, acceleration is defined as the time rate of change of velocity. But there was a problem during Galileo's time, how to define acceleration or change in velocity, whether with respect to position we can define, or distance, or with respect to time. So how to define acceleration, whether with respect to position or with respect to time? This was a puzzle or confusion during Galileo's time, but he was intelligent enough to make a conclusion after doing series of experiments on freely falling body and body moving in an inclined plane. So doing these two experiments, freely falling body in a straight line and in an inclined plane. Inclined plane. This is theta inclination. He could conclude that change in the velocity. What was the conclusion of Galileo's experiments? Conclusion was that the change in velocity is constant of time. Constant of time. Okay. So that's why acceleration can be universally defined change in velocity with respect to time. But if you define change in velocity with respect to position, it is not a constant. Okay. So change in the velocity with respect to position is not a constant. That's why we cannot universally define acceleration as change in velocity with respect to position. So Galileo concluded that the time rate of change of velocity is acceleration. So we have learned that acceleration is time rate of change of velocity. Again, we have learned in the previous two classes, velocities, there are different velocities like average velocity and instantaneous velocity. So average velocity and instantaneous velocity, these two types of velocities we have seen. And see, acceleration is rate of change of velocity. That means we can define two accelerations here in this case also. So one will be average acceleration. So one is average acceleration, average acceleration, and another one is instantaneous acceleration, just like velocity acceleration. Okay. Now one by one we'll be learning and we'll try to represent graphically how we can represent. I'll just clean this. I'll just get average velocity. So how do you define average velocity? So average velocity is the change in the velocity, change in the velocity. It is defined. So average velocity is defined as change in the velocity in an in a in an interval of time. Interval of time. So I'll just give you explanation for this sentence. So change in the velocity in an interval of time is actually average acceleration. So average acceleration is written as a bar. Now suppose an object is moving with the velocity moving with a velocity v1 for t1 seconds. Okay. Or in other words, it has velocity v1 at t1 second. Okay. So v1 velocity, the object is moving with v1 velocity for t1 seconds, and the object is moving with v2 velocity for t2 seconds. Then we can define average acceleration mathematically. So v2 minus v1, this is the change in the velocity, divided by interval t2 minus t1. So if we write in terms of delta v divided by delta t. So this is the mathematical expression for this average velocity. Okay. Now I'll just clean this portion. I'll show you the velocity time curve which we had already seen in the previous slide. if we want to calculate the average acceleration for this curve, velocity time curve, look how we can calculate the average acceleration. Suppose I want to take the interval C, interval delta t is equal to 10 second. That means 0 to, so t1, suppose my t1 is at 0 second and my t2 is 10 second. 10 second. Okay, t2 my 10 second. So what are the velocities? At 0, the velocity is 0. What is the 10? Look here, 10 goes like this and touch here. You will see somewhere, if you look here somewhere, it is here or like this. It is like this. So it is 20. Okay, 24. Sorry, 24. So the average acceleration is v2 minus v1. So 24 is the v2 and v1 is 0. So change in the velocity 24 and divided by, this is 10, t2 is 10, t1 is 0. So what is the average acceleration you get? You get 2.4 meter per second. Okay, so I have forgotten to tell you the unit of this. See, since this is delta v by delta t, this will be change in the velocity is meter per second, unit is meter per second. Again here it is second. So ultimately your unit will be meter per second square. Meter per second square. So this is your unit. So meter per second square is the unit for the acceleration. Now I'll see another interval that is from 10 second to, so 10 second. See, this is my t1 now, 10 second, and t2 is 18 second. Here, look here, t2 is 18 second. And if you just do what I had done earlier, for 10 it goes up to 24. Okay, like this. And for 18, you look here, it is same. For 18 it is same. Okay, so 24 will go something like this. Okay, something like this value. So both 18 and 10, so they both have actually this, at this portion this is uniform velocity. Uniform velocity, that means at t1 second or 18 t1 second, the velocity is 24 meter per second, and at 10 second also it is 24 meter per second. So if you just want to calculate the average velocity, sorry, average acceleration, so how do we do? Similar fashion, v2 minus v1 divided by t2 minus t1. Okay, so this gives rise to 0 because it is uniform motion. So when an object, so what is this? This is acceleration, average acceleration 0, which means when an object moving with a uniform or constant, both are same, constant velocity has 0 acceleration, whether it is average or instantaneous. The 0 acceleration has 0 acceleration. So this is what it is implying. Okay, now I'll just see another interval, like t1 is 18 and t2 is 20 second. So if that is the case, so what is the average acceleration during that interval? So t1 is 18 and t2 is 20. So see, at 20 the velocity is 0 over here, velocity is 0. So final velocity is 0, initial velocity is 24, okay, and see t2 is 20 and t1 is 18. So here you'll get 2, here it will be 20 minus 24, so you will get minus 24 meter per second square. This is how you can find out average acceleration from a velocity time graph. Okay. Now the question is whether we can plot this. Yes, we can plot as well. Look, till 10 second it has a uniform acceleration or average acceleration which is about 2.4. See, you can see that. So it is actually increasing. Sorry, not increasing. This is having average acceleration till 10 second. Till 10 second it has 2.4 meter per second square. Okay. Then when you see during 10 to 18 second, during that time it has zero average acceleration. See, look this part. This part has zero acceleration here. Okay, zero acceleration. Actually, this is uniform motion. This is actually we are plotting average acceleration versus time curve. Okay, not the position time or neither. This is a velocity time curve. So this has actually zero acceleration means uniform velocity that we have learned in the previous figure. From the previous figure already we have learned that. Now in this last interval you look, the average acceleration is negative 12. Okay, see, this is a negative 12 value, and during, see, between 18 to 20 second, during this 2 second interval of time, it has constant or average acceleration, that is minus 12. So this is the value. Now what is the instantaneous acceleration then? So we have learned what is average acceleration. Now we'll see what is instantaneous acceleration. So what we have learned here, average acceleration is the change in velocity over a time interval. So this gives the change in the velocity, information about the change in the velocity over a time interval. Now this is the graphical representation for average acceleration for the velocity time curve, which we have already seen. Now we'll see what is called instantaneous acceleration. The instantaneous acceleration can be defined in a similar fashion. That is, the instantaneous acceleration at any instant of time is defined as the limit of average acceleration. So limit of the average acceleration as the time interval delta t becomes infinitesimally small. See, this is the mathematical expression. So we know average acceleration is del v by del t. Now you take the limit of this and bring your time interval delta t towards 0. Then what you get is called the instantaneous acceleration, which is denoted by simply a, and in the language of calculus you can write this as total time derivative of velocity with respect to time. So this is what the definition of instantaneous acceleration. Okay, now we'll see few points about instantaneous acceleration or this acceleration itself. Okay, so before that I'll just go to the previous slide and show you how do we define instantaneous acceleration. In acceleration time curve, okay, versus time curve, okay, from here. So in this case you look, we have found out 2.4 acceleration for the time interval 10, but instantaneous means at each instant it should give. So what is the acceleration at 0 second? It is 0. And what is the acceleration at 10 second? It is 2.4 over here. Okay, 2.4. That is the acceleration. And now, actually, I should not say at 10, because at 10 it becomes again 0. Exactly at 10 it becomes 0. I should say up to 8 second. At 8 second it is 2.4. Okay, since it is uniform acceleration or average acceleration at any instant of time for uniform motion, or I can say that instantaneous acceleration at any instant of time is the value of average acceleration at that particular instant of time for a uniform motion. Okay, now exactly at 10 it becomes 0. Acceleration becomes instantaneous acceleration 0. And see, till 18 second it is 0. Just after 18 second it becomes minus 12. So as you just go from 18 to 18.5 or 18.2 or 3, it becomes exactly minus 12 meter per second square. And what is the acceleration at 20 seconds? Actually, you look when you just go from 18 to 20, that means you are just reducing the reducing the interval. That means when you come from 19 point, suppose 95 to 20, so till this time you have minus 12 meter per second square instantaneous acceleration. Even at this instant you have this much acceleration, but exactly at 20 second it becomes 0. Acceleration becomes 0. Okay, exactly, see here it is. So this is how. Okay, we'll be actually taking numerical examples and various graphical problems in our quiz session, which you might be finding out in our websites. In addition to that, also we'll take one class for numerical examples for this particular topic, when I'll be discussing many other graphs. Okay, so now we'll see some general comments about acceleration. So we have we have seen that we are calculating or defining the acceleration as a change in the time rate of change of velocity. And since velocity is a vector, and it has both magnitude, okay, magnitude as well as direction. It has both magnitude and direction. So acceleration means change in the velocity. That means what? Either it can change in magnitude, or it can be changed in direction also, or maybe both. So acceleration, you may find out acceleration if the magnitude changes. Okay, magnitude changes of v changes, or you will find out acceleration if the direction changes, direction of v changes. Okay, or if both happens, both, then also you will get acceleration. Okay, that means when both the direction and velocity, magnitude, direction and magnitude of the velocity both changes, then also you will find out there is an acceleration. I'll just give you a simple example when we get acceleration just by changing direction. Okay, we know if the velocity magnitude changes, suppose 12 meter per second, it changes to some 20 meter per second, you have the change in the magnitude, so you'll get acceleration for this case. But what if there is always a velocity constant but direction changes. I can give you a simple example, that is circular motion. In circular motion, suppose an object is moving in a circular path of radius some r radius, and you may not know now, we'll learn it in planar motion or motion in plane. That time we'll discuss again what is circular motion. Circular motion, in case of circular motion, there is a centripetal force which always acts towards the center. Okay, the object actually traverses in a circular path, and during that motion always the velocity becomes perpendicular with this force or acceleration. So velocity will be always perpendicular to this acceleration, or in other words, the velocity will be at any point of this curve or any point on this circular path you take. It is actually the direction is along the tangent direction at that particular point, but the magnitude remains the same. Direction is changing continuously. Look here, it is like this, but the magnitude of the linear velocity is always constant. Velocity is magnitude of the linear velocity constant, but see the direction changes. Here also magnitude is v, the direction changes. Okay, now if I calculate the acceleration for suppose these 2 points A and B. So look, this B, or see A, I take this as x cap or I cap direction, and left hand side this as minus I cap direction. So suppose my initial point is at A and final point is B. So what is the change in the velocity? Change in the velocity is not 0. Okay, change in the velocity you have to write in terms of vector here. Okay, so if you write in terms of vector, look what is the change in the velocity. Change in the velocity will be, see, initially I'll be writing final velocity, this I cap, minus of v minus I cap at this particular point A. Okay, so you will get actually 2vi. So this is the change in the velocity. Okay, so you will get acceleration from here. Because of the change in direction of the velocity itself, this centripetal acceleration is arising. Okay, this acceleration is called centripetal acceleration, which is coming due to the change in the direction or unit vector of the acceleration in this circular motion. Okay, all right. So now, since this acceleration is a vector quantity, any vector quantity can possess either 0 value, okay, or it can possess a negative value. So acceleration can possess these values, either 0, it can be negative, sometime it can be positive as well. Okay, we'll try to pick up. Okay, so we'll try to show you in the position time curve how does this 0, negative and positive acceleration look like. Okay, so we'll see in the position time curve xt curve how does position time curve look like for 0 acceleration, for negative acceleration, for positive acceleration. Look here, see, it is upwards, so it has positive acceleration over here. So it is positive acceleration in the curve A, position time curve. In the position time curve, so x versus t curve here. See, this is down this way. So the acceleration actually negative for this curve. So you will be sometime given a curve, like if in the multiple choice type question, there will be 4 curves. You have to find out for which the acceleration is negative, for which the acceleration is 0, and sometimes they will ask you for which the acceleration is positive. So you should remember, or you should learn it like what should be the xt curve for negative acceleration. So this is the one negative acceleration, and for this is actually uniform motion. If you can shift the origin and look here, this is uniform motion. I have discussed in the first day itself. It goes through origin. If there is some initial distance already covered and then starts the motion, then you will have shifted position. It will not touch the origin, but it will go, it will be a straight line. Okay, it will not go through the origin if it has some initial distance. Suppose the object starts moving from 10-meter towards x-axis. Okay, in the along the x-axis. So up to this it is 10 meter, and thereafter it is having a uniform motion. Actually, you can see the straight line actually meaning uniform velocity or uniform motion. If there is uniform velocity or constant velocity, in that case the acceleration will be zero. Both average and instantaneous will be zero. Okay, so now we'll try to get the graphical representation of a car which is moving with constant acceleration. So when I say constant or average acceleration can also change. That is topic of higher class. So in our study, we'll take an average or constant acceleration in our discussion of kinematics or laws of motion or anything in this book. Okay, constant acceleration. So constant acceleration means average acceleration. Look what we have defined. Average acceleration is this. Suppose, so this is v2 minus v1 by t2 minus t1. Suppose my v1 is 0. Okay, at t1, at t1 0. That means we started with 0 velocity and from 0 second. So this can be written then or I'll just write, I'll not take 0 initial velocity, I'll take initial velocity sometime will be denoted as u. So I'll write that as u. This is u at time t1 is equal to 0. So this can be written as, and maybe v2 will be writing as v at t2. Okay, t2, t is equal to t2. This is t is equal to t1 is equal to 0. Okay, so then this average acceleration, expression for the average acceleration can be written as v minus u y. t2 is actually t, we are writing t2 is t, so it is t. So what we get from here, you look, acceleration is equal to, average acceleration is equal to final velocity minus initial velocity divided by time interval. Like that also we can define. Now you look here, from here, if you know the initial velocity, if you know the time interval, and if you know the average acceleration for acceleration of motion of the object, then you can easily find out what will be the final velocity after certain interval. So how to do that? You'll get as this as u plus average acceleration or constant acceleration into t. With this expression you can find out. Okay, anyway, what we are trying to understand or see now, that acceleration, various type of acceleration, like positive acceleration, negative acceleration, zero acceleration in velocity time curve, velocity time curve, velocity time curve, velocity versus time curve. Okay, let us see. So look this one, as I said, at t is equal to 0, it has some initial velocity v0. Then it increases uniformly. It increases uniformly. It is not a constant velocity. Constant velocity means like this. So it is not constant. Velocity is increasing. See, the slope is a constant one. So that means it has a constant average velocity. Sorry, constant average acceleration, and that acceleration is positive because the velocity is increasing up to some positive value. V02 velocity becomes V02 V, because we have seen final velocity will be V is equal to U plus constant or average acceleration into t. So after some time t, the velocity is increasing to certain value v over here from v0. That means it has positive acceleration. Okay, positive acceleration, and it is increasing. Positive acceleration. It is moving with positive acceleration, and the acceleration, sorry, acceleration is in the positive direction. Okay, so positive acceleration. So for the case of positive acceleration, velocity increases. So v increases here. Okay, all right. Now I'll just get the curve B. Look here. This is the initial condition, initial case. At t is equal to 0, the velocity was v0. Now at t is equal to t, the velocity is somewhere here. That means your average acceleration, if you write final velocity v minus of v0 by time interval 0, sorry, t to 0. That means look here, v0 over here is, so this will be a negative acceleration because your, so this is v0 minus of v0 minus v divided by t. So it is having negative acceleration. All right. So it has negative average acceleration. Acceleration is constant because this is having a constant slope, but slope is negative. That's why it is actually having negative acceleration. And you look here, the final velocity v is less than the initial velocity in this case. All right. Now let us take another car. See, look this case. Okay, in both the cases, this one, A and B, it is moving in the positive x direction. Positive direction. Okay, it is moving. Both are in positive direction. But in this case, look in the C, the object is moving in the negative direction. Negative direction. And also from the slope you can understand this is a negative acceleration. Negative acceleration. So the velocity will be decreasing, that means increasing in the negative direction. Okay, so this is a negative acceleration and the motion is in the negative direction as well. The last one is this. Look, in this case it is very peculiar. So till t1 second, 0 to t1, it is actually moving in the positive direction, but with negative acceleration. With negative acceleration. Negative acceleration. Okay, negative average acceleration or constant acceleration. And as it crosses t1, see, look, this portion, this is negative, in the negative direction. So after t1, object is moving along negative direction. Negative direction. Okay, and obviously you can see there is no change in the slope, so it is moving with the same negative acceleration as it was moving with the acceleration in the positive direction also. So same negative acceleration it will continue with, but the direction changes. See, I can give you a simple example. Suppose a car is moving in a path with constant acceleration, then it has taken an like a U-turn and then goes in the opposite direction. So this actually is represented by this particular curve D. So in the curve D, it is actually turning. There is a turning at t1 second. Okay, it is turning. There is a turning. So turning, when there is a turning, you'll see this kind of curve, and obviously it is moving with the same acceleration in both direction. Okay, both in positive and negative direction. Okay, so with this we'll stop it here. Next day we'll take up kinematic equations and related problems. Okay, next day we'll meet again on Tuesday. We'll learn that day kinematic equations and problems. Okay, related problems in next class. All right, so thank you for your patience. I'll stop it here now.